So yes, we're on Curtis Street at the Curtis Hotel. My name's Curtis, so I'm going to hug the cube. So.
We only need to get a picture of it. You can use it.
No, I'm going to use this. It cuts down on the hand waving too, so that's a good thing with engineers. Okay, so context. So what you heard from Ellis earlier was a multi-year project, the second half of which got us back up. ASD 100 started getting us off of COTS hardware. ActiveStar Ultra finished getting us off of COTS hardware and revamped a large part of our architecture. That was a multi-year project, started small and then ballooned to take over all of engineering, and now is G8 and shipping, right? So what I'm going to talk about here is the next big project, and it's going to start small, and eventually it will balloon out and take over all of engineering, and then we'll ship it. So the reason I'm going through that context is there'll be small features in between. This will take a while to gestate. This isn't a next year's deliverable. This is something that we're starting to work on. So I'm just setting your expectations that I'm going to ask a lot of questions about whether the direction I'm heading is going to resonate with you and your workloads. And then based on that, we're going to fine-tune the architecture and then go build it, right? And I'm going to be in booth number 225, so come by and I can talk to you in a lot more detail about where I think we're going with this. Okay, so data center of the future. So first order of magnitude is, what is the data center environment going to look like in 5 or 8 years? And what kind of product would we need in order to fit into that data center to meet all of its requirements and common expectations? So that means we have to predict what that data center is going to look like so we know where we fit. I've been saying for a while that the HPC has a set of best practices that, like infinite band networks or Ethernet networks and particular ratios between storage and compute and GPUs and batch queuing systems and a whole bunch of other things that are normal in HPC. Those are unique to HPC because the enterprises and the cloud people don't do that. What we're seeing is HPC is adopting some of the cloud technologies. We've heard, I think TGS earlier this morning said that, maybe that was a lunch conversation, said that their data centers are going to look very cloudish in the future. That's I think Ramesh also said that it's a shared resource center. There's lots of customers inside their organizations come together and want to share the single common compute cluster and its storage cluster. So that's sounding like the requirements of a cloud. The workload automation systems are very cloudish as well. But at the same time, there are enterprise requirements coming in, like real snapshots, and one of my favorites is in AI, self-driving cars. How do you defend yourself against a lawsuit? By saying that you trained your AI according to best practices. Right? Now, well, how do you do that? Well, you have to document how you got there. That's data provenance is showing that you got the right data, you managed it well, you filtered out all the bad stuff. There's a whole bunch of other things that will come along, I think, in terms of evolving the HPC data center future requirements for it. Okay, so highly mixed workloads changing over time. That's a staple in public clouds. It's also a staple in shared resource centers for HPC. AI is just the big thing. AI brings a new it's sort of the poster child for one of the new requirements of latency. Traditionally, HPC was all about bandwidth. Latency has been a small component of the requirement for a while. Now that's growing. AI is going to make it more intense. Where the latency actually comes from is the GPU. It's so expensive, it needs to be kept busy all the time. And so you have to, and there's a basic level of randomness inside the I/O workload for an AI environment. So it comes down to there's a latency requirement. Decreasing sophistication, we see that because it used to be that the Fortran programmers wrote their software knowing what the parallel file system could do for them, and they optimized for total wall clock time. These days, the genomics guys are my favorite example. They don't care. They don't care what the storage system can do. They create millions of small files and just expect it to go fast. So this is our opportunity, our challenge and opportunity is making all of that supporting all of these different trends in the market and providing a better product that helps solve the problem. Okay, how are we going to respond? Ludicrous Mode, you may have heard us talk about that. This is the name of a project. It's not the name of the product when it ships. That's up to the sales guys and marketing. But I like the name Ludicrous because it's a representative of extreme acceleration, and that's what we're focusing on. So we need to retain our high bandwidth, workload, mixed workload, low TCO. All those things are a hard requirement because those are core values for the company. We're going to add the capability to support ultra-low latency workloads and metadata-intensive workloads. We need to stay with COTS hardware and portability. Those are also core requirements for the company. Now, so the rest of the presentation is, okay, that sounds great. How are we going to do that? Right? Sure, that sounds easy when you say it like that, but it actually is kind of hard. So let's peel the onion one layer. What are the actual requirements that we think we're going to have to go through? We need bandwidth and latency in the same namespace, the same file system, the same administrative domain. So there's one pane of glass that you use to manage all of it, and the application writer is going to see a same POSIX file system, but some of those files need to be in a position to be latency sensitive, to support latency sensitive IOs, and some don't because they're just bandwidth related and they need high bandwidth instead of latency. So we need the right performance profile for each workload. We also need burst buffer style absorption of writes. That's a special case that's been handled by other people. We want to bury that in this overall project of what we're trying to do. Very fast metadata, at least for the things that are stored inside the latency tier. And if you need very fast metadata accesses, then you can promote things to the latency tier. I'll describe more detail what this means in a second. But of course, the hardware has to be controlled and monitored and managed by Panasas. We don't want to make your life difficult by saying, oh, there's this extra piece of hardware you have to fiddle with, and POSIX. Now, one of the things that makes this tractable is commodity NVMe over Fabrics boxes. They're wonderfully fast, very low latency, seem wonderful, except if you go out and look around, all of the ones you can buy, except for about 2 or 3, don't come with software on them. And once you get down to the bottom of them, an NVMe over Fabric box is no different than a fiber channel disk array. It's just faster. Right? Well, what do you need for a fiber channel disk array? A file system. Oh, that's where we come in. Right? But that's sort of defining our challenge. Now, Brian and Ellis and I, we've been arguing for a little bit about exactly how we're going to do this. I'm going to go through one of the ways we can do this. It's not a commitment on how we end up actually doing it, because this is going to be data-driven. We have to do a lot of prototypes and experimentation. So the OSDs that Ellis has poured his heart and soul and sweat and blood into is going to continue in this particular view of the future. That's our bandwidth tier. I personally am skeptical that it's tractable to take a bandwidth tier and also make it low latency. So the reason you're seeing this kind of structure is because I'm starting with the exploration of, okay, if we leave that alone and we use the Fabric box, and that's where our latency sensitive tier storage is, that seems like we've preserved our investment and we haven't messed it up by trying to fix it with latency, and we're putting our latency bet on another tier. The directors need to coordinate everything between the two tiers, obviously. And so there's a whole bunch of engineering challenges, and I'm going to go through some of that. Again, not a product commitment. We have to negotiate and figure out, well, how do we really do this? The best leverage and the best eventual supportable structure. Okay, so the next couple slides are question and answer, sort of. It's conventional wisdom is pessimistic. Oh, well, you just need all flash for that at $1,000 a terabyte. Excuse me? You just parallel file systems, they're high latency. You can't change that. Right? So I'm going to go through a bunch of those and try to provide arguments that say it's at least plausible that we have a shot at addressing that concern. All flash storage is always the answer. Simple foremost, at the capacity points, it's just too damn expensive. $1,000 a terabyte is huge compared to 200. The specials at 150 bucks a terabyte. Let me just leave it at that. You could manage that fabric box as an LRU cache. I'm skeptical that that's the right answer because LRU is an algorithm that works if you're doing repeated use of the same data. The first time you access something, it's slow to bring it up into the latency tier. And then if you hit it again, great, sure. But what workloads re-hit the same data every time? Well, some not, right? AI is not, an AI application doesn't want to pay that first access latency. They want to keep the GPU busy all the time, even on the first access to a piece of data, for example. So it doesn't seem like that's the right answer. We also want lots of small files to have their full life cycle happen inside the latency tier. Create, read, write, unlink, all of that in the latency tier because there are workloads that include lots of small files. They want to be fast. So I'm laying out arguments why it's not just an LRU cache of some things. It needs to be managed differently. Right. So we need a tier. So parallel file systems are high latency. Ultra is not particularly high latency. The metadata being stored in a database on an NVMe drive means that type of metadata should be fairly fast. Now, there are things that need an analogy that I've used in the past for the Ultra project is that it's a ship going through the ocean and it creates a bow wave. That it's so fast that it's going to be pushing the rest of the software around in order to keep up with it. So the director software, we have not taken had the time yet at this point to go through and optimize all of that software in order to take full advantage of Ellis's work, right? So our latency should be good with the OSV version 4 software and the optimized director software. The challenge is that that's going to be good latency, not ultra low latency, right? My view of architectures is you shoot for a near impossible goal, knowing full well you're going to fall short. If you shoot for an achievable goal, you're going to fall short and you won't get what you want. So you shoot for really high, right? So I'm shooting for ultra low latency, and then we'll negotiate, we'll figure out exactly what it is we can achieve, what's a reasonable risk-reward ratio. Yeah, yeah, but Ludicrous, see, I'm on the Ludicrous team. We do ludicrous things. It's just, okay. Ultra-low latency is really hard to do. Well, yeah, but not if you plan for it, right? NVMe over fabric boxes are ultra-low latency. And why are they? Why are they able to do that? Because they planned for it and they didn't focus on anything but low latency. Another one of my reasons for thinking that leave the bandwidth tier alone, add a latency tier. But, so if what you have is basically a fiber channel disk array, and you don't want to mess with any of the software between the application and that fabric box, so you don't really want to go over the network to a director to get permissions to come back and then go down to that fabric box, what do you call that? Well, there is a design paradigm, a design model from the late 90s called a shared file system. There is a raft of examples of them out there. So that's an interesting model. We'll explore that. We'll find out if that really has legs that can take us to where we want to go. The challenge in a shared file system is not actually high performance for a client accessing a directory and a whole set of files. The challenge is in multi-host sharing. So if I have 1,000 computers all accessing different directories, well, that's straightforward and relatively easy as long as you know what you're designing for. The challenge is if I've got 1,000 computers and they're all writing to the same file, well, that's hard. While reading from the file, that's fairly straightforward too, right? So these are the challenges in this particular architecture, and we need to find out what we can do to offset those challenges. This is one of my favorites. POSIX is slow and doesn't scale, said by all of the object bigots out there. So there's a key difference here that's POSIX defines inodes and directories. It does not define allocation groups and super blocks and everything else on this list here, right? And those are the things that actually slow it down. POSIX, the vast majority of POSIX operations affect one inode. Out of the 100 million, billion that are in your file system, that's embarrassingly parallel, right? The worst possible case defined by POSIX, a cross-directory rename involves 4 inodes out of hundreds of millions to billions of inodes. So it's not POSIX per se that's the problem, it's the underlying file system structure. Okay, so now, following this logic, if I haven't made a mistake in my logic, now we know what to go attack. It's not POSIX, it's the representation of the POSIX. POSIX is the payload in a data structure, and now I need to modify that data structure so that I can achieve my goals. Now, one of the ways that's important characteristic here, in local file systems today, or just in file systems in general, there are the ACID properties. Atomicity, consistency, independence, and durability. So I take an action, that action has to be atomic. It has to be consistent that we go from a consistent state in the file system to another consistent state as a result of the transaction. Independent, if I'm making a change here and making a change there, if they're not defined to interact, they shouldn't interact. They should be independent of each other. And durable, as soon as the transaction commits, then it'll commit for everybody, everyone sees the result, and it's durable. Well, if we can relax durability, then we can achieve some of these goals. We can separate POSIX from file system metadata. A whole bunch of detail, I can tell you in the booth how I think that might work. But it's interesting to note that tier 0 scratch is in fact that relaxed durability. Tier 0 scratch, you create a bunch of files, and there isn't a hard guarantee that those files will survive in the event of a failure. Right? That's what tier 0 scratch means colloquially to all of us. And so that's why I'm holding out hope for that there is some there down this path. Some there. Policy engines are required for tiering. Yeah, good policy engines are hard to build, so don't build one. Right? Everyone here has a batch queuing system, a resource management system. It has pre-triggers and post-triggers. You can say, oh, here's the data files I'm going to need to read, here's the ones I'm going to need to write, and I want to move them into the latency tier. And when I'm done, the post-trigger moves them back again. Right? So what that means is we can treat this as working set storage, rather than, I've got 500 people all queued up waiting to use the cluster, but only 20 jobs are currently active, and the queuing system can move the stuff that needs to be latency sensitive up before the job starts. It crunches away on it, move it back automatically afterward. Because we're going to own the Fabric hardware, we're going to own the management of it, we're going to own the consistency of the data going into the Fabric box and back out again. Right? I should say boxes, because it's not just one. Right? We'll support many of them.
I would look at CNs for current or prospective Panasas folks
Yeah.
that think that their users would do this when they're writing PBS jobs. Because this is one of my major. I worked on PBFS before it was OrangeFS and Argon, and we had a bunch of hints similar to this, and nobody used it. So that was researchers doing this. And I'm just worried. One of my major concerns is will people actually take advantage of this to use this expensive resource?
Well, our schedule is proprietary, so
Proprietary.
if I could force them to use it, they will use it.
So we can't hear.
Yeah, okay.
Sorry.
Sorry, please.
I would hope this would be. This one. It's not on here.
Turn it on.
Oh, here, use this one.
I'm getting the cube.
Oh, yeah.
Yeah. Our scheduler is proprietary, so I would hope that if I convince the correct people that it would be baked into the scheduler, because that's what I'd like to see. When they queue up their jobs, it would do this in the background. The processors would not even know it was happening. It would just happen. So.
Okay. So in my enthusiasm for the thing, I said I was going to ask a bunch of questions, but I didn't actually do that. So I'll save the questions for the end, because this is almost done, and then we'll go through a bunch of is this smoking dope or whatever, right? Okay. So conclusions. It seems to us that there is a need for more than just the bandwidth. We need to make a big investment, like we did with OSD version 4. We made a big investment in order to get ourselves more than current, but to leapfrog ahead and have something that was going to be class leading for another 5, 10 years, right? So we're trying to do the same thing with latency and ideally with metadata as well, metadata intensive operations. Now, if you want to scan the metadata for the entire file system, then there's a different solution here. If you're talking about a metadata intensive job, that's what this is targeting, right? Rather than a file tree walk across the entire file system. That's a slightly different thing here. And then we're working on it. We're currently in prototyping and exploratory mode, trying to understand what the constraints are and what architectural approaches are going to work. I've described one of them here. So, having said all that, as Ellis said, let me go back to questions. Does it seem to you guys that are actually users of HPC systems, administering them, that the premise is right, that these changes are happening to the workloads? Okay, so I heard some confirmation. Is it going to be a big deal, latency and high metadata like small file operations? That's going to be a major part or a little part, or yeah, we know that AI is coming and we think there might be an issue, but we're not quite sure what it is yet.
It's growing for us, and it's going to continue to grow.
You want to?
It's growing for us, and it's going to continue to grow.
Okay, good. Continue to grow, good.
This year, next year, 3 years from now.
Okay.
It will be.
Will be, okay, good, good. Does anything in what I've described set off your BS meter? Just sort of a broad question, right? Saying, yeah, that's not going to work. You're just full of it, right? Patents, yeah, patents. Rajesh. Rajesh, sorry. Yes, excuse me.
Does it have to be this or that? Can we have a dial of sorts where you can tune your performance, whether you want high latency or low latency or somewhere in between, or is that?
What we have thought about so far, so the interesting question. What we've thought about so far is the bandwidth layer. If the data you want to access it in a sequential kind of way, then it just stays there. We said, okay, we'll move things that need to have low latency up to the layer of hardware that's capable of low latency, rather than trying to shoehorn latency onto the OSD tier. Now, so your question is, can we have something better than binary choice, one layer or the other? Maybe. The NVMe over fabric boxes are sort of the highest performance tier because they're expensive. We could provide lower tiers, lower performance, but the OSD version 4 stuff with its NVMe and SATA SSD and hard drives are actually pretty good at what they do. And so I don't have an answer for you. It's a good question. I'll think about it. I don't have an answer at this point. Other questions about anything?
Why did you pick NVMe instead of like 3D Xpoint or some of this other stuff going on?
I asked questions about this kind of approach at SC 16 and 17 as well, for that matter. And but it was in the context of the direct flow client, the software that lives inside the compute nodes. What it does is it arranges for cache coherency. It POSIX compatibility, cache coherency from the point of view of that node. So if you put an NVMe drive in that node, we could potentially make the contents of that NVMe drive coherent with the rest of the realm. And so we talked about that a lot, but it finally dawned on me that putting it in the node meant that if that node crashed, any local modifications that you made to that were then gone until the node came back, if it did, right? So you wanted a disaggregated solution. You wanted it over fabric rather than in the node or the other. That's the same challenge with Crosspoint and with NVDIMMs inside the node. It's isolated. If you want if you're planning for the case where the node might be down for a day or permanently, then you either have to say, I'm going to synchronously replicate that data to another node, but going over the network is going to destroy the performance advantage of the Crosspoint DIMM, right? So or you start talking about relaxing the durability and you sort of go down this path. So that was the rationale we used for not just starting with cross-point and saying, oh, this is the answer here, because it was disaggregated on the network, as well as sharing, right? AI, if you have a distributed training application, you've got 100 nodes that are learning from a data set. You want one copy of the data set. You don't want 100 copies. There's a cost of moving the 100 copies. There's a cost of storing the 100 copies. And so again, that's an argument in favor of disaggregation. So,
Curtis in the back.
please.
I couldn't quite hear the comment earlier, but it sounded like there was pushback against having the hooks in the batch system. And I think
Yes.
that is going to be one of your challenges.
Okay.
That one of the advantages you have now is it just works.
Yes.
Users don't have to care about what tier they're on. They don't have to set striping. None of that garbage.
Right.
Putting that little hurdle in there takes away one of your current strengths.
Okay.
So I think that could be a challenge.
Yep.
The other one, I think you said something about relaxing the data integrity.
The durability,
The,
right.
the durability.
Right.
So does that mean you're not writing any parity for that to that tier 0?
Yes, in this tier 0, right, we would not be doing the erasure coding. That we'd be doing aggressive transfer of the data out of the. In this view of the world, the clients are reading and writing to the fabric box, but the directors are also reading and writing to the fabric box. They're preloading the data, but they're also looking at the content and pulling modified data out. Take a snapshot in the fabric layer, and they will drain that snapshot down to the underlying storage, and as a way to reduce the window of risk, right? So yes, the current thing that we're exploring is, what if we didn't do erasure coding at that layer, as both a performance and a latency advantage, but also, but then counteracting the disadvantage by this aggressive write back.
Okay, so I think that also goes against one of your current strengths of
Okay.
the data integrity story.
Right.
So you would have to build some parameters around that said, after X minutes, it's guaranteed to be durable.
Okay.
Or you can issue some other operation, like a user in their job can say, I want to make sure that I don't complete this until it's durable.
A sink or a flush kind of equivalent, right?
Yes.
Okay. Okay. Cool. Thank you for the feedback. That's what one of the things I was hoping to get out of this is to make sure that I didn't end up building something that was, oh yeah, you forgot this, right? That would be tragic. Other questions or comments, suggestions? Cool. Thank you very much.
Thank you, Curtis.